In this video, we're going to explore how to smooth some of the COVID case data that we've seen in an earlier example. And the basics of it are fairly straightforward for loading. This is all standard stuff. We're going to have a data file which contains a general pool of the information, daily information across the world of COVID cases, new cases, deaths, cases per million, and so on. So what we're going to do first is get the Canadian data set. So COVID Canada is equal to the COVID data set, where the nice thing about countries is they're very well standardized. We have ISO codes, International Standard Organization codes, which is equal to, sorry, let's go COVID at ISO code equals Canada. And we'll do that. And let's do a quick head on that so we can see what we've got. And we see, yes, indeed, we got Canada. And these days are days in 2020. So this is January 1st is day one. And so nothing really as exciting is happening yet. But what we see a little bit later to get some plots going is we can do a plot of the COVID from Canada. And we're going to plot the day against the, let's say, new cases. And we're going to do that. We'll do it first like that. COVID can here. There we go. And this time series is pretty long and pretty short. So what we're going to do is change the figure size here so it's more stretched out. Take our usual 15.5. There we go. And so there's, this often actually looks a bit like sound data. If we look at this from a very abstract perspective, we see some sort of periodicity going here. There might be some fun things in the Fourier transform. That's not what we care about today. What we care about today is recognizing that this data really is a sequence of dots. This is a vector of day values. This is a vector of new case values. And what we'd like to do is smooth this out or generate a trend. And one of the things we talked about earlier is that we've got, or typically used in the news, is this idea of a 5-day rolling average or 7-day rolling average. And what that means is what we have is our function, our signal, is our COVID Canada new cases. And I'm just going to do this complete conversion here. There we go. So to match our earlier symbolic representations, f of t is our signal. It's this thing here. And the other ingredient is our g. What we're going to try to do is get a smooth version y. All right, so we've got our f. To get our g, what we want is like a normal, actually, let's do the 7-day average that we did before. For that, we would say, let's go t equals a range, NP array, actually NPA range, here we go, from -3 to 3. Let's double check what that looks like. Oh, right, we need to go one higher, so 4. All right, so those would be our values. And in principle, our g is just equal to 1 everywhere. So let's do it as np.1, this bracket length of t. And then we'll print g. Oh, wait, it's not 1, it's 1/7. So let's divide by the length of t here. There we go. So what we'd have is on the values from -3 to 3, we'd have 1/7, 1/7, 1/7, 1/7, 1/7. The idea is if we pick any point in the center of this graph over here, look 3 to the left, 3 to the right, we want to average those together. That's what the convolution will do for us. It'll sort of move this g function, which is basically take 1/7 over 7 numbers, and move it along this whole graph and generate that moving average. Now here's the gotchas. We can't use the Fourier transform, which is what we really would like to do at this point, to help us, because we need a sequence, our g sequence, to be the same length as the signal that we have. Well, that's a drag, but it's totally doable. In fact, what we just do is we just change our strategy here. Instead of going from -3 to 3, we're going to need a g that's actually, let's start off all zeros actually, for the length of f. So we're going to tweak this all around a bit here. Length of f with another bracket. There we go. So now our g is the same length of f. And what we could do here pretty easily. We're going to start counting at 0. So the first, second, 0 first 1, 2, 3 there, or what we want. We can build an alternative t value here, which is np.range, length of f. Let's take a quick look at that. Print t. There we go. So t starts at 0, goes 1, 2, 3. Perfect. G goes 0 all the time right now. And what we want to do is just make these first 3 numbers, or where g, the g values where t is less than or equal to 3, make those equal to 1/7. Okay. And that did not work at all. Oh, yes, it did, because I put the print statement in the wrong order. Here we go. There we go. Print g. So it's a little more tedious now, but we can see that we've captured that, those 4 numbers there for 0, 1, 2, and 3 indices. But conceptually, I want to go back. I want to go back 3 more. Here's where we get back to our theory about real sequences and Fourier transforms. If I want to go back off the end here, the way I accomplish that is I go to the end of the sequence, because all of these sequences are assumed to be periodic, or underneath the hood, whether you think about it or not. When we're taking sines and cosines building the sequence, it implies that when we stop here, we actually restart the same graph and it goes back up and again. Or going back this way, it would actually go back to the top and do another arc on this end. So that's implicit in our assumptions. So if I want my g function to be just 1/7 around 0, well, the other side of around 0 is up at this back end over here. Fortunately, Python gives us a way to handle that, which is the negative notation. So we can say -3 up to, and we don't specify the end. What that's going to do is tweak these last 3 values here, the third last, and then all the remaining ones. And so we're going to set those equal to 1/7. Run that. Get our print statement back in so we can actually see it. And there we go. So the way to think about this is a little counterintuitive, but think of these as being on a ribbon where we have 0, 1, 2, 3, stuff. By the time we get to here, it's -3, -2, -1, and then 0. Oh, that takes us back to the start again up here. So what we have is a nice version of our weekly average. And we should probably tweak this a little bit so it's more general. Think about, how many days, 5 days, 7 days, and so on. We can tweak all that with this code here, just changing our g function. So we have our signal, which is complicated. We have our averaging function, which is mostly 0, except for these few non-zero values around the 0 index. And then we can do our transformations. So what we're going to do is do a convolution of those 2 things, but we're going to do that in our Fourier space. So we're going to do our FFT of f, and our g hat is the same thing for g, and then this is the awesome thing, do the convolution. F hat times g hat. This is just a regular multiplication, element by element. If we take that, we're going to get our smooth signal y hat, but it's transform. And let's just run that and make sure it works. Okay. And then y is just the inverse transform. So we do careful to make sure it's the inverse transform. And let's do that. And we'll just do y. We'll just print y here. Okay. So it ran. And if you take a careful look at the complex numbers here, notice they're all very, very small. They're all 10 to the minus 13. They're basically not there. So let's just do a print out of the real values of y. And what we get there are some high numbers for a second, and then we get values that are small and small, small and small and small. We'll explain why that little discrepancy at the beginning is where it is. But what we can do now is plot our, let's do our same figure size here. plt.figure, fig size equals 15 and 5. So we're going to plot our f, days against f, and let's make that our blue dots. And then we're going to plot our days against our y value, our smooth version, in red. And leave it like that for now. Oops. And it wasn't day, it was still our COVID Canada day. I never actually spun that off into a vector, so there we go. Okay, we get this little warning about complex values. All right, we didn't, we used our y value. Let's get rid of this print statement. We didn't take into account that y is still complex, even though the real parts are really, really small, because we essentially have a real signal, but some numerical round off, and ta-da! There we have our averaged signal. But hold on, let's do a quick little analysis here. Again, mostly we would plot these as lines, so very typically this would be how we interpret this. It's worth noting we still have spikiness going on. 7 days hard rule, nothing outside of 7 days is really an awkward thing to be doing mathematically. So it's easy to explain to people, which is why it ends up being a common usage. But the things that we want to notice as well are little artifacts that appear when we do this. First off, these little lines here at the end, and this end here actually where it drops down. And just as in any case, if you'd imagine doing this by hand, when you get to the end and say, well, I'm going to take the average of 3 more data points, but there are not 3 more data points to take an average of, you'll often see the graphs kind of cut off manually at that point. And we probably should do that for ours as well. The reason for this artifact is for the same reason as building our G, we looped around. When the Fourier transform is doing these calculations, it's also looping around. So it interprets this data set as having new cases that are going up and up and up. And then immediately afterwards is 0, 0, 0, copying these guys here to the other end of the array. And that's not really what we want. But also, again, at this end, we couldn't really take an average over 7 days anyway, so we'd probably just cut that off as well. So you can imagine putting an extra layer of indices in here saying only go from 2 to -2 or something like that. I'll leave the syntax for that up to you. But that would be one example of how we can build a smoother that uses the Fourier transform. And just again, think about how you would do this with code if we were trying to build this red line, or again, more accurately, this vector of dots represented by the red dots. Doing that with loops actually is surprisingly complicated. Whereas here with the Fourier transform, we just FFT both things, literally multiply the coefficients in the Fourier space, and then take an inverse transform. And we've got our smooth version. In fact, just because I can't resist right now, what we're going to do is tweak this and make it a 13-day rolling average. So 6 and 6, and we'll divide by 13 and divide by 13. And if we do that, and do that again, we should get something that looks much smoother. Well, not much smoother, but smoother. And we certainly see that those irregularities, the little spikes that were there last time, are smoothed out. There's still some interesting stuff happening here. That's again just because the harsh borders, I think, of including or not including this point here in the average. As soon as we get more than 6 days on one side away from this point, the average drops down. So you can see some advantages to a smoother smoothing function than just this in or out categorization. But we also see the penalty of trying to use a smoother or wider window, which is when we get towards the end of our series or the beginning of our series, well, we can't really trust those averages anymore because we can't consistently apply that same rule of 6 on either side when we get to the very ends of our data set. So that gives you some idea for how we can use a convolution, or why we'd use a convolution here for smoothing, and secondarily, how we can use the Fourier transform to help us achieve that on real data.